Hello everyone and welcome. In this video we're going to be answering the question, can the grid handle electric cars? We're going to kind of take this question to its extreme. Let's say if gas cars were to be banned, not whether or not that's a good decision, but if that were to happen, could the power grid actually handle all of these cars being electric, an immediate switch to electric cars? And so I really think there's two parts of this question. You need to look at big picture, looking at power production, and then smaller picture, looking at residential consumption, where you're actually charging all of these cars. So let's start off with a little very simple math. So in the United States, there's about 230 million licensed drivers. And those drivers drive on average about 13,500 miles per year. So you can multiply those two together and get the total miles driven by people in the US each year just in their, regular old everyday cars. Now, the way we discuss efficiency for electric cars is kind of silly in the US, but we give it mile per gallon equivalent, MPGE. And so the worst electric cars are getting about 70 mile per gallon equivalent. The best electric cars are getting about 140 mile per gallon equivalent. And so if you look at that spread, if you look at the median, it's over 100 mile per gallon equivalent. So in this video, we're going to use 100 as our, just average point that we're looking at, probably a bit conservative and certainly a number that could increase in the future. But let's just say the average electric car gets 100 mile per gallon electric. Now, what does that mean? Well, 1 gallon of gasoline is equivalent to 33.7 kilowatt hours. So if we go back to our initial proposition, we have our 230 million drivers. They're driving 13,500 miles per year. We divide that by their fuel economy, which is 100 mpge, and then we multiply that by the amount of energy used, and that gives us the total amount of energy that would be used in the US if everyone was driving electric cars for all of their mileage. Now, that number ends up being about 1 trillion kilowatt hours. So total amount of energy that would be needed if everyone was using electric cars, about 1 trillion kilowatt hours. Now, that doesn't take into consideration transmission losses through power lines, and it doesn't take into consideration charging losses when you're charging that battery at home. So we're going to add another 25% on top of that. So a total amount of energy required of 1.25 trillion kilowatt hours. Now, how much energy do we actually produce in the United States? Well, according to the EIA, about 4.1 trillion kilowatt hours. So we would need, in addition to that 4.1 trillion kilowatt hours, another 1.25 trillion kilowatt hours. So an increase of total energy production in the United States of about 30% would be required, which is significant. I don't think it's as mind-blowing of a number as some people might have thought. Switching over, just a 30% increase in energy required. Now, let's give some perspective for that number. So from 1960 to the year 2000, in 1960, the energy production in the US was under 1 trillion kilowatt hours per year. In the year 2000, it was nearly 4 trillion kilowatt hours per year. So in 40 years, we increased the amount of energy we produced in the United States 5 times. And so this is asking for a 30% increase, not multiplying that number by 5, just 30%. And it's over what duration? So if you start looking at what are countries saying that are going all electric, they're saying, maybe 2050, some maybe 2040. GM announced, they want to go all electric by 2035. The whole point being, if you look at what the US was capable of from the years 1960 to the year 2000, they were increasing energy production by about 4% per year. So in order to get this 30% improvement, if we were to use a similar scale looking at 1960 to 2000, it would only take us 6.5 years in order to meet that demand, to make the amount of energy, additional energy required. If every single person were to start driving an EV, we'd have 6.5 years based on previous rates. But, I don't think we're going to adopt anywhere near, we're not going to be anywhere near 100% EVs in the United States in 6.5 years. It's going to take much longer than that, especially considering we're only adopting at like a 2% rate currently. That meaning 2 out of every 100 cars sold in the US are electric. So the adoption rate's very slow. The switch over to full electric is going to take a very long amount of time. It's not going to be this instantaneous thing. And so for a 30% increase in energy production, that to me doesn't seem like a challenge. Does it mean companies have to make more power? Yes, absolutely. But are companies willing to make more money? Yes, they are. If you are a customer and you want more energy, that is a product they are selling. They will sell you what you want. So you want more energy, they'll sell it to you. I don't think that is an issue. Now, I will say that 30% increase does not take into consideration population growth or other reasons why you might need more energy at home. So a production, a power production company, it might not be 30% that they need to increase by. It could be more considering, what the population growth is going to be, if it's explosive population growth, or if you have other demands for electricity that are not accounted for currently. Okay, so now let's look at it from more of a local perspective. So of course you have that power plant that's generating the electricity, and then it sends that to a transformer, which steps up the voltage and sends it across transmission lines, so you can send that electricity very far distances efficiently. So then you get to a local transformer, you step down that voltage and you distribute it across local power lines, and then before it comes to your house at that final pole, you have one more transformer to step down the electricity before it gets to your house. So now we're at your house, and so the question is, how much energy are we going to be adding to our household consumption by adding this electric car? And so if you look at the average house in the United States, according to the EIA, electricity consumption is about 900 kilowatt hours per month. Now, if we go back to our example of driving 13,500 miles per year, well, then we can get an average monthly consumption of electricity purely from that electric car. And so that gives us about 15.6 kilowatt hours per day, or about 475 kilowatt hours per month. So that means an increase in total consumption on a monthly standpoint of about 50%, and that is a sizable increase. So, this is going to, cause a strain on a local grid. And so think about it like this. If you think about it from an average standpoint, all that's saying is, you're using 1,400 kilowatt hours per month. That's the equivalent of using one outlet, one 120 volt outlet, constantly. So can the electricity grid, on average, handle one outlet from every household constantly? Absolutely, yes, it can handle that. It's just like running a vacuum cleaner constantly, but that's the only thing you're doing all month long. So of course the grid can handle that. The challenge is that's not what happens. So if everyone's driving an EV and they all get home at 5:30 and they all have fast chargers at home and they all plug in, their car at 5:30 and everyone's got an 8 kilowatt charger, and suddenly all of these houses in a neighborhood are all charging at that really high rate, well, then you're putting a huge demand on that local electrical infrastructure. And so from a power standpoint, it's not that big of a deal. It's only 2 hours on average that you would need to charge each day in order to accommodate the average driving distance per day for the average person. If you think about it like from an AC standpoint, it's like running an air conditioner for 4.5 hours per day. Like, that's definitely something that happens, right? There are plenty of houses that are going to run an air conditioning system for 4.5 hours per day. That's the amount of energy you're asking for. The challenge is you're asking for it all at once. Now, speaking of air conditioning, of course, there was a time where air conditioning wasn't common in most households, and then there was a time where air conditioning was common in most households. And we didn't simply say, you know what, the grid can't handle it, let's all just sweat in our homes. Like, we rose to a certain challenge, that challenge being, hey, we need more energy if everyone wants to use AC in their homes. So, it has been done. And there are solutions, infrastructure solutions to these challenges. And it's not like we just have to give up and say, we can't do it. It's like we've done it before with, bringing air conditioning into our homes. So what is the solution? Well, there's multiple parts to this. So first of all, yes, you could just simply update the infrastructure to allow for that higher demand peak surge in power consumption. Now, sure, that's possible, but it'd be a very expensive thing to do, and it means that your electricity rates are all going to go up really high because the power company has to make all those expensive updates. So there are smarter ways of solving this problem, and the real key is just changing when everyone is charging. So, for example, a lot of peak demand occurs when everyone's running their AC systems, right? But during the night, when temperatures cool down, not everyone's running their AC systems at full blast like they were during the day. And so energy consumption at night goes down. So utility companies can say, hey, if you charge your car at night, we'll offer you a cheaper rate. A lot of people will take advantage of that cheaper rate, and thus more people will charge on off-peak hours. And as a result, the peak demand doesn't change all that much, and therefore your infrastructure demand doesn't change all that much. Another example, let's say you live in a location that has a lot of solar power. And so of course, solar power is only effective during the day unless you have some way of storing that energy. So a solar company could say, hey, we're going to give you a better rate if you can charge during the day when we have crazy power production. And at night, when they don't have that production, then you're charged a different rate because something else is kicking on in order to compensate for that. Now, does that mean everyone has to do it? Everyone has to charge during the day? No, you just need a certain percentage to take advantage of it so you can reduce your peak demand. So it's all about just making sure that that peak demand remains as low as possible. And you can do that by spreading out when people charge. You could also have smart grids where you have certain areas of the grid where you allow for charging, and then you move to another section of the grid and you allow for charging. And it can work as long as you spread it out so that everyone can get that full charge. Now, maybe, people don't want to be in that system, so you make it opt-in and offer a lower rate. So you say, hey, you can control, my peak power limits, and as a result, you'll get, a cheaper monthly electricity bill. So you can have ways of getting a portion of the population. It doesn't have to be everyone. A portion of the population to opt in, and by having that portion, incentivized to opt in, you reduce your peak, and by reducing your peak, you don't have to change the local infrastructure nearly as much because it can handle it. It can handle those constant loads. It's where you get those spikes, like what you see in California, where they have factories that aren't producing power, factories that are down, and then really high outdoor temperatures. Everyone's using their AC. In that scenario, there's going to be brownouts and blackouts because they can't produce all of that power and send all of that power out immediately. The peak demand is so high. And so, yes, you do have to update that infrastructure or these flaws will be shown. But it is something that is predictable. It's something that you can see, okay, here's the EV adoption rate, here's how many cars are coming in. It's a problem that doesn't seem like, hey, this is the reason why we can't switch over to EVs. That's not going to be the grid. The grid can handle it. It's a predictable problem with a predictable solution. And there are clever ways of minimizing how much infrastructure you have to update. Now, a really interesting example of this is Norway. And so Norway has a very high EV adoption rate. In fact, in 2020, over 50% of new cars bought were electric. So an insanely high adoption rate. So you might wonder, well, what's going on with the grid? And before you think, okay, in Norway, completely different circumstance. Yes, sure, it's a lower population, 5 million population of Norway versus, 300 million in the United States. But the problem is just scaled differently, right? Like they still have to produce a certain amount of power for those 5 million residents. And if they all start going EV, they have to produce more for those residents and distribute it more for those residents. So it's just a different scale of a problem. It's the exact same problem though. And so with Norway, if you look at their energy consumption numbers from 1990, they've only increased by 30%. That's pretty wild to see. So that's not that dramatic of an increase in electricity consumption, yet they have this massive push towards EVs. And really, the bulk of that increase in consumption comes from an increase in population, because if you look at it on a per capita basis, per person, you can see that the energy consumption really hasn't changed throughout the years. So they found other ways to be efficient while adding on these other, additional power draws. So, if you make your home AC unit more efficient, but you're charging with an electric car, then, you may have offset that charging by the more efficient cooling system or heating system. So Norway is an example where you can look at today and say, look, they've adopted at an insanely fast rate. Like this is not the rate that the US is ever going to come close to adopting at, and yet Norway is doing it much faster, and they are able to, meet these challenges from an energy production and distribution standpoint. It's also worth noting, that electric cars can improve in efficiency in the future. So, we're not at their best. I'm using an average of 100 mpg, where we have examples today of 140 mpg. So electric cars can improve in their energy efficiency. And of course, you have that charging efficiency, which, is in the mid 80%. So there are ways that we can improve, that power consumption and those peak demands. Now, there is one thing, though, I do want to make very clear about this video. I'm not saying that I think, it makes sense to tell everyone today, as in right now, hey, you have to switch to an EV. There's obvious challenges. Electric cars are expensive. The cost to purchase them new is very high, so you can't simply expect everyone to be able to do that. And then secondly, the charging infrastructure isn't there for everyone. So if someone lives in an apartment and that apartment doesn't offer any way for them to charge their car, it seems silly where one of the biggest advantages of an electric car is the fact that you can charge up at home, and then you tell someone who can't do that, hey, you have to drive this thing. So there are very real challenges with electric cars. The purpose of this video, I really want to dive into that, power grid question. And I think that's a bit of a silly excuse to use to not adopt EVs, saying that the grid can't handle it, because it is predictable and there are predictable solutions in order to make that happen. Are there challenges with EVs? Yes, absolutely. So if you'd like to watch other videos that I have surrounding electric cars, I'll include some relevant ones in the video description. Thank you all so much for watching, and if you have any questions or comments, of course, feel free to leave those below.